today's lecture topics: Abelian algebra, general linear group, check that Jacobi's identity holds in GL of V, and metric version of GL of V. So in today's lecture, I will be doing Abelian Lie algebra, etc. etc. And today's lecture number is 19, right? Because 18 I have done yesterday only, and this is chapter 4, right? So Abelian Lie algebra or Lie algebra, however you pronounce it. Now, what is an Abelian Lie algebra? Any vector space V has a Lie bracket defined by this x comma y. This is the Lie brackets, right? And x comma y is equal to 0 for all x comma y belonging to V. This is called Abelian Lie algebra. Now I will explain you all this. Now any two vectors having this Lie bracket is equal to 0 is called Abelian Lie algebra. Okay? Like this way you all have to study. See, these are the two vectors because for all x comma y belonging to V is what? Vector space, right? So any two vectors, like see, there are vector spaces in the Lie bracket. Any vector spaces in the Lie bracket is equal to 0 is called Abelian Lie algebra. Okay? In particular, the field F may be regarded as a one-dimensional Abelian Lie algebra. Okay, so do this definition properly and I'll go to the next definition. Now, general linear algebra. Now, what is a general linear algebra? Suppose that V is a finite dimensional vector space over F. Okay, let GL of V. Now, this is, we denote this as what? General linear algebra, right? So, denote the set of all linear maps from V to V. This is again a vector space over F. And it becomes a Lie algebra. Now this thing becomes a Lie algebra if we define the Lie bracket, this Lie bracket by what? We should define this Lie brackets by this. Lie bracket of x comma y is equal to x composite y minus y composite x for all x comma y belonging to GL of V. Where this composite thing, it denotes what? This zero round thing, it denotes the composition of maps. Okay, it is a composite. Okay, here. Now this Lie algebra is called the general Lie linear algebra. Okay, so this definition is very important to solve the problem. Okay, to solve this problem. Now you have to check that Jacobi's identity holds in GL of V in general linear algebra. So general linear algebra, so Jacobi's identity, now we have to check whether our Jacobi's identity holds in GL of V. That means general linear algebra. Okay. Now we have to show that this thing is equal to 0. This is the Jacobi's identity which is equal to 0. We have to show that. Okay. Now take the Jacobi's identity first. That is Lie bracket or Lie bracket of x comma Lie bracket of y comma z, close the bracket, plus y comma z comma x in the Lie brackets, then plus in the Lie brackets again z comma x comma y. Now what you'll have to do, this is equal to what? Now I have taken this y comma z first. Okay, first write x composite. Now do this part for this one. How it is? Take this thing. What are the brackets says? X composite y minus y composite x, right? So similar way we will be doing for this. Y composite z minus z composite what? Z composite y, right? Then minus we have to do for this, no? This composite this, then this composite this. So minus y composite z for this one minus z composite y composite this x. So using the definition of that composite thing. Now plus, do it for this one, similar way. Y composite, then Z composite X minus X composite Z. Minus, so similar way do for this one also, minus what was it? Z composite X. Which one I was doing for this one, no? Z composite X. Now this Z composite X minus X composite Z. This part into Z. Y. Then plus, I am doing for this one now. Z composite, for this one it will be what? X composite Y minus Y composite X. Then minus this composite Z, right? So X composite Y minus Y composite X composite Z, okay? Now for this, you all have to know this definition of the general linear algebra to know, so that you all, so it will be easy for you all to do this problem, okay? Next, I'll turn the page. Now what will happen? Now this is equal to what? X composite Y composite Z, right? How you got this? Now this X composite you have to multiply with this, as well as you all have to do with this, okay, along with this. So same way with this and then this with this one, and similar way you all have to do for this, okay? Now X composite Y composite Z minus X composite Z composite Y. See this, sorry, this with this I have done, then minus, now this with this, minus Y composite Z composite X plus Z composite Y composite X plus Y composite Z composite X minus Y composite X composite Z minus Z composite X composite Y plus X composite Z composite Y plus Z composite X composite Y minus Z composite Y composite X minus X composite Y composite Z plus Y composite X composite Z is equal to 0. Now the terms will get cancelled, all the terms will get cancelled, and finally you will get 0. So here we have proved that the Jacobi's identity holds in GL of V, okay? So everywhere what you all have to do, this you all have to multiply with, meaning along with this, and this will come along with this. Similar way, this will come with this will come with this, right? But when this comes with this, it will be negative. When this comes with this, what will be happening? Minus into minus will become positive along with this. So I hope you all have understood, and this part is very easy. You all can do this. I have already explained. Now the third part is what? 3 dash. We have done 3, right, of this. This is the third part, and the derivative part, meaning 3 dash, not derivative. Here is a metric version, okay, that 3 dash now. That is the metric version of 3 actually, that first part which I have told you all. Now GL of V I have told, no, now this is the metric version of that. GL of n comma f denote the vector space of all n into n matrices over f with the Lie brackets defined by, now here the Lie brackets are defined by what? X comma y is equal to, there was a composite over there, here slight change is there, here composite is not there, xy minus yx without composite, okay, where xy is the usual product of matrices x and y. This is the usual matrices for x and y, okay. X and y is the usual product of the matrices. What I mean to say is that. So here this is what? Metric version without any composite thing. Remember this, it is similar to GL of V but without composite thing. Okay, next I'll turn the page. Has a vector space GL of n comma f has a basis consisting of the metric unit Eij, where 1 is less than or equal to I, j is less than or equal to n. Here Eij is n into n metric which has 1 in the ijth position and all other entries are 0. It can be easily checked that EIJEKL is equal to delta JK and delta ILEKJ, where delta is the Kronecker delta. This I'm done with today's lecture, and the next lecture I will be doing more exercise problems. And okay, I hope you all have understood. If you all have not understood any of the part or concept of today's lecture, you all can just comment below. Feel to ask. I can even if you all have not understood, I can again explain you all and can upload the lecture again. Okay, and thanks for watching.